Yeah, hello everybody to today's e-seminar on multiphysics simulation of MRI systems. So, MRI systems, we want to get a three-dimensional image from nuclear spins. How can we do that? And I guess I don't need to talk too much about the background here, but just as a very brief reminder, we basically need an overlay of three different magnetic fields: a very strong and highly homogeneous DC static field, a low frequency gradient field for getting a 3D image, so for the spatial encoding, and finally a radio frequency pulse that really excites the spin so that we get a response and can create an image of it. The technology itself is known since the 1960s, so many years, but still there's a lot of design ongoing and we have continuous design challenges. It's driven by various different things, but mostly by 2 points. On one side, we try to drive the strength of the DC field, of the static field, higher and higher in order to get a better signal-to-noise ratio. And at the same time, we want to make MRI examinations more convenient, so we try to get larger bores. So I was talking about three different magnetic fields. Why are we calling it a multiphysics simulation e-seminar in that case? So what are we going to talk about today? So we do have those gradient coils. They are available for the X direction, for the Y direction, for the Z direction. And around the gradient system, we do have the main coil, which is creating the strong static field, and an active shielding coil to avoid too strong magnetic fields outside of our MR system. Even though we do some active shielding, in addition to that shielding, we may have some external passive shielding in the treatment room as well. And as we are really talking about extremely strong magnetic fields, we will also, now I have a freezing here. Okay, we will also see very strong mechanical forces on those coils, which naturally will lead to some deformation of the coils as well. And since we can achieve these high static fields only by superconducting, we also have an effect of quenching. So we need to make sure that our magnets stay to be superconducting. If not, we may have a serious damage in our system. Additional to those static and low frequency magnetic fields, we do have the RF coil, the radio frequency coils. You see a typical example here. In many cases, we have multi-channel systems, which in addition require some circuit for tuning and matching our system. And from such a simulation model, we can, for example, analyze implant safety inside an MR system. But instead of just using simple phantom models, we most likely want to see also the actual heating inside the human body, because we want to avoid any damaging or hurting of the human body. And finally, to round off our multiphysics range of simulations, we may also want to see not only the magnetic fields, but how is the image in the end looking like. So we want to do a proper image simulation.